This final year project will be discussing the design methodology on a timetabling problem. The goal of this project is defined as to formulate a novel workload model by incorporating different constraints, a course allocation algorithm to improve the teaching workload distribution and satisfaction metric, and a second algorithm to perform timetable scheduling to benefit the various stakeholders. To first create a novel workload model, we need to quantify workload framework that can be used in timetabling problem. These constraints are teaching, administration, and research work of a faculty. The model also need to cover different weightage parameter on various teaching events. The base teaching contribution is calculated as such. Workload credit of a course event is computed with the teaching event parameter multiplying the event size, novelty factor together with hours conducted per week and the amount of weeks per semester. Using this sample data. Here is an example. Given a course has a size of 300 students, with 2 hours of lecture a week, 10 tutorial groups of 1 hour per week and 5 of 2-hour lab session, we can derive each individual teaching event's value, and the total workload credit is the summation of each teaching events. Secondly, we can formulate the research relaxation for each faculty by using a base parameter multiply with total summation of staff engaged by the faculty and the staff parameter. An example of a faculty supervising 2 postdocs and 1 research assistant will give the faculty a research relaxation of 5%. Lastly, the administrative component of the workload model is classified into 2 parts. Firstly, each faculty is employed with various service hours. Hence, the relaxation tier is grouped by the amount of hours they are engaged. Secondly, there are some faculties holding administrative appointment in the school. They will be granted an additional relaxation. Using the 3 components derived, the summary is as such. Total teaching workload is equal to the summation of all the course's teaching events workload. Total teaching contribution is the summation of the faculty's teaching contribution minus the summation of the total faculty's research relaxation. With these values, we are able to get the average teaching workload by dividing the total teaching workload with total teaching contribution. Using the average workload, we can find the optimal workload of each faculty by simply multiplying with each individual teaching contribution. Now, we look at the first algorithm, simulated annealing, to solve the faculty course allocation problem. Here is the formulated problem. The objective of this algorithm is to approximate a near-optimal solution, ensuring there is randomization done in the process, restricting the size of input data to ensure lower computational complexity, and to fix the problem with an input given by customizing methods to create a fair and intuitive heuristic. Here is the pseudocode of the algorithm. The algorithm will first formulate a base solution. Next, the solution will be refined over a period of time based on the temperature cooling rate. In this phase, each new proposed solution will be compared with the previous solution by an acceptance policy function. If the new solution is better, the algorithm will take it as the current solution. Lastly, when the temperature reaches stale state, the final solution will be returned as the near-optimal solution. Now, we will look at the second algorithm, genetic algorithm, to solve the timetable scheduling problem. The formulated problem of the timetabling scheduling is as such. Hard constraints is defined as limitation that the algorithm cannot violate. They are not allowing a student and faculty to attending or conduct 2 classes at one timetable slot, having a class that exceed the venue capacity, and using an wrong venue type to conduct a class. An feasible optimal solution can be lenient on soft constraints violation. We define the soft constraints by improving the amount of work days for both faculty and students. Similar to algorithm 1, the genetic algorithm is built based of 3-part logic. In base solution formulation, the algorithm create a pool of random solutions. Next, add solution refinement. It will select 2 different timetable schedule from the pool to create a child solution, mutate, repair, and evaluate the fitness of the child. The idea of this algorithm is to improve the pools of solutions like a genetic evolution. It will return the best schedule where all hard constraints are resolved. Traditional approach of the allocation tends to result with faculties being severely overloaded. With the implementation of simulated annealing algorithm, we see an improvement of workload variation. Standard deviation dropped from 40 to about 20%. Similarly, the genetic algorithm also resolve hard constraints violation from manual scheduling. Both runs also resulted with faculty teaching for less than 4 days. The additional day freed can be used to conduct research work or performing administrative duties. To conclude, the two algorithm methodology provided a more fair and intuitive faculty course allocation and clash-free timetable. This will then provide an optimist timetable for faculties and students.